Welcome to the pre-recording of this first part of the session number 8 in the 8-week summer course. This is labeled as lecture 15. We are also closing off the first 3 weeks in our 8-week summer session. So I introduced lambda in passing in a Jupyter notebook earlier, then just saying that if you have a small function, you don't want to give it a name, you use lambda. But there is more than just that can be done, that lambdas are actually adding some very cool features to your programs. I will also Lambdas also play an important role with list comprehensions when we map functions to lists. So functions in Python are like functions in mathematics, but they are so much more than that. We have seen that you can change arguments of functions when they are passed as references, when you put a bracket around the arguments. You can use functions to store data. So we can make a remember table. So the function can, for example, remember the number of times it was called. It can also remember the arguments, or it can remember what it computed and when it has computed it. So this is a very powerful way to work with functions. Since this is kind of a milestone, I think most of our lectures are actually milestones, but since we have already arrived thus far in this course, I will recap what we have done for Python or in Python as for programming in the small, as we could say. Making the link between the control structures and the data structures. Okay, let's go through the slides. So we had our little guessing game. So there are a couple of applications that run through this course. One could see programming as also a little bit storytelling, that we have some problems that we have solved and we can solve them in many different ways. I'm using the many different ways to introduce very useful features. So in the guessing game, there might have been somehow, I mean, it's just a small game, but it actually guessing secrets is important. For example, the security of computers. The guessing game is also the password authentication. So what is actually uncomfortable in our previous solution to this problem is that the secret was kind of stored explicitly. Instead of storing the secret explicitly, we will use an oracle. So an oracle can tell us true or false without actually knowing much about the secret. The oracle goes back to antiquity, but it also happens still very often in everyday life. Often we know what something is when we see it, but we can't really define it or even describe it. This is also something what the oracle here does. So there is in pseudocode, there is an oracle that generates the secret. The oracle is a function that is computed by the function generate secret. So the number will be generated there in that generate secret. But as soon as the generation of the secret ends, the number disappears. So these functions, they have local variables and they are volatile, very volatile. So as soon as the lifespan of the function is over, you don't really know the value of the number, but the function that was made still can check against the value of the number. Um, and that will be called. So in this repeat until loop, in the pseudocode, the user is prompted to make a guess, and the guess is given on input to the oracle, and the oracle will return true or false. So if the oracle returns true, then the loop ends, otherwise the user is prompted again. So this can be implemented using the lambda keyword. So if you are in the habit of giving Greek letters or Greek names to your variables, you cannot use lambda because that is reserved. Here is the broader context. So if you are curious how an operating system actually saves passwords, well, the password is generated. So often your browser will generate a secret password. Uh, and that should be scrambled enough so that you can never actually remember it after you saw it, unless you have a very special memory. But typically, when the user types in a password, a user that is user-friendly, the user can remember it, then actually the encrypted password is saved. So the encryption algorithm is something that the authentication or that the verification algorithm calls on the user input. So the user input is just a local variable that disappears immediately after the password verification ends. So the operating system then essentially stores only the encrypted function, the encrypted value. And this encryption typically works as a trapdoor function. So it's not just a simple cipher like you did in the last quiz, replacing characters by other characters, but it is typically a function for which it's very hard to compute the inverse. It's very efficient to evaluate, so the password verification goes very quickly, but even if you would see the encrypted password, it would be very difficult to go back. So that is a trapdoor function. So you get very quick answers out of the oracle, but the oracle actually doesn't really know much about the nature of the question. It can only tell you right or wrong. Okay, list comprehensions is actually something that you know it when you see it. So in this course, indeed, often we introduce a lot of examples. And it's also a little bit after seeing many examples that actually you know what it is. So a list comprehension, I said this is a for in a loop, a for loop in a list. It's a way to make lists very quickly or to make new lists from given lists. One typical application is to apply a function to all the elements in the list. And so here you have a given list L, and we make a new list R by mapping the function f to all the elements x in the list. Often this is used in conjunction with conditional expressions. You can make lists smaller that way. So if you have a list of numbers, if the remainder after division equals 0, division by 2, then the number is an even number. So with the conditional expression here, we can actually select from a list of numbers all the even numbers. So conditional expressions, they are if statements. So I said a list comprehension is a for inside a list. but it can also contain an if inside the list. So it can be a little bit longer, and there can be multiple fors as well. Um, so the if test is used to filter elements. So we have the for, the if, and then we also have the zip. We can make new lists, and in particular, we can make lists of tuples. If we take two lists of the same length, zip them, then we apply the list construction of that. Then we have a list of tuples. And this could be very useful to reduce lists to a single element. So for example, if you want to sum all the elements in the list, you can take the first half of the list, slice it. You can take the second half of the list, then zip them. Then you have a list of tuples, and then you apply the plus to all the elements in the tuple. Seems far-fetched, but this recursive, so you recurse, you continue with this, you iterate the process until you have lists of two elements. But this often leads to a very quick, and can also lead to a parallel algorithm to compute sums very quickly and also very accurately. There are fewer steps, so you are done in the two logarithm of the length of the list, so it can do quicker. And when you do quicker, you also have fewer round off. So these are three important ideas here, in connection with list comprehensions. We map a function to a list, we can filter a list, and we can zip a list. I will give examples in the second part of this lecture. Here is already one example. So one running application on one important algorithm that we have used already in several lectures is the simulation. So simulation consists of uh, taking samples and then counting the number of successes. For example, the number of successes here um, counts so we generate random points within a square, within a unit square. We count the points, every point is a success when it's within the unit disk. And the number of points of the total amount of points that we generate that lie inside the unit disk, they will actually approximate the area of the unit disk. If we do this between 0 and 1, we have to multiply by 4. So you can see I tried, I explained it in words and hand-wavingly here. In mathematics, it goes a little bit shorter, so there are 3 bullet points here in mathematical notation. You can see that the functional implementation with list comprehensions is actually not that much longer. The underscore is an anonymous variable. If I do not want to give a variable, because I'm actually not using a variable here, then I'm using this underscore here. It may be that if you do this with trillions and trillions of numbers, that you do not want to look at all the numbers in the list, that you actually do not want to store all the points. But for visualization, it could be useful. Okay, functions can store data. So we have seen that functions are like mathematical functions, except when you are passing lists, or as we will see in the second part, we can also pass a dictionary to the function. Here is a very small function, 3 lines without a documentation string. So there is a default argument, an empty list called data. So if you are out of inspiration for good names, data is always a good name. So how does this work? When we call this function for the same time, for the first time, a list is generated. It's an empty list, and that is assigned to data. So the very first time we append to that list data, but and the next time that list is still there because it is an argument data. So this is where the von Neumann picture of a computer still is very useful, and knowing in Python that lists are actually references. So the very first time we actually allocate, or Python allocates memory for this and returns a reference. In the Python terminology, data is assigned to a reference of a list. But that happens only once. So the data, so what is inside the list, changes all the time. So we are actually adding new names to each time when we new references to each new items. So what the item really is the function doesn't really need to know this, but when it prints it out, you can see the evolution of the list of data elements. So the slides illustrate this. This is a very versatile mechanism. I will give an example with dictionaries. So it looks like a programming trick, but you can use it. I will use it also to give another version of the guessing of a secret. We may now be very uncomfortable that the secret number is really secret in the past with that oracle. We can store the secret in a data in such a default element. And the first time when there is no data, the secret will be generated and stored in that default argument. Functions that store data have all kinds of benefits. For example, if you have a library that you export, you can, for example, count the number of times that function is called. You can also store the number of operations that that function executes if you're interested in the computational cost of a function. Uh, we can also use this to remember the outcome of a computation. So sometimes a function can be quite expensive to run, but the second time when it's called, it will actually remember the outcome, which is also very useful. All right, so we have reached somehow a milestone with functions. Um, we have Python is very extensive, and actually, if you know a very small subset of the language, you can already write very general programs. So one textbook that when I was given, when I was learning to program, is this textbook of Niklaus Wirth. The title is Programs are Algorithms plus Data Structures. Um, I would rather say now that algorithms are control structures and data structures. So in any algorithm, you would write an algorithm as a sequence of statements. So it's an ordered set of unambiguous steps that are executable and that lead to a terminating process. So we have the three basic control structures that are kind of mirrored by the data structures. Some algorithms are driven by the data structures. In a data structure course, you should see heap sort, and the structure of the heap, the algorithms to insert and to remove items will actually determine the sorting algorithm. When we get to the second part of the course with object-oriented programming, it are actually the data structures that are often determining how a program is going to behave. Okay, now this is a hands-on course. We learn by doing. Um, the list comprehensions. So it's often very good to uh, see the examples so we can generate tuples, lists of tuples. This is very useful if we want to generate, if we want to define dictionaries. So the first exercise is one example where you would list all kinds of fractions rounded to two decimal places. In some sense, the first exercise is a warm-up to the definition or to the evaluation of the exponential function. It also has the factorial in there. The factorial is something that was encountered earlier. The factorial of k is the product of k of the integer k with k minus 1, k minus 2 up to 1. We generated points inside the unit disk. You can also generate random points on the unit circle. This could be useful if you would want to approximate the arc length of the unit circle. So this could be an alternative way to estimate pi. You generate sufficiently many random angles and you kind of make this arc length, sorting the angles then. Um, so this also, so the purpose of this exercise is that it reminds you of the polar representation of points in the plane. So you will generate random angles and apply the cosine and the sine function. So this is applying on a list of numbers, on a list of angles here, applying the cosine function, applying the sine function. And you can verify that within the machine precision, all the numbers will actually satisfy the test x squared plus y squared equals 1. We will end with the secret guessing. So um, I will end the Jupyter notebook with that example. In the last lecture, I indicated that adding a verbose option is typically very good programming practice in your programs. So you could essentially add an option, a general options dictionary as a last argument in every function that you write. And you actually can define as a programmer inside the function the options verbose, but also feedback or debug, give more extra information when in the debug mode. Here with the feedback mode, the guessing of the game would allow for larger secrets, where the user would be given too small and too large feedback, so there would be a message printed, depending on whether the secret not just true or false, but whether it would be too small or too large. So you would have a more useful oracle. Okay, I have prepared Jupyter notebook, so I'm at the half of this 50-minute lecture. I will scroll through it, although for practical purposes it might be good to actually also run it. So here is the making of an oracle. So we can have functions that produce functions on output. So this is a function that generates a secret. So it's a random digits between 0 and 9, 0 and 9 included. So the NBR here is a random number. It's a local variable. So when I execute this function, so when I'm executing this function inside a Jupyter notebook, apparently nothing happens. But the Python interpreter doesn't give any errors. So there are no syntax errors here. So that's also in some sense the virtue of testing out your functions in a code cell of a Jupyter notebook. You can actually call the Python interpreter and get some feedback. The Oracle returns a function, so actually I can probably illustrated that um, last time, but everything in Python has a type. So you see that it is a function, and I can call it. So if I don't have any information about the Oracle, about the feedback, so the Oracle just returns me true or false, then actually I have no choice but trying all the possibilities. And for my sake and sanity, I can probably, the best way is to do this one after the other. Now, doing things one after the other. So this is a function, this is a lecture on list comprehensions. So I can call the oracle for all the numbers in the range. So here this is another list comprehension where I make a list of integers. So if I don't have the oracle there, I am listing all the integers starting from 0 up to 9, but I'm applying the oracle function to it. Now this is just 10. I can see that the number is 8, but I can actually, or actually I'm sorry, the number is 7, because that gives me the index of the true. And I made actually a mistake. This should have been range 10. So you see, I often still make that mistake, that range ends one number before. So it gives me the opportunity to recall one of the useful um, intrinsic operations, as we call them on lists. So the list is part of the standard library. The list comes with the operation index. So here I only have 10 numbers. I can see that it is at position 7, but if you do this with a million numbers, it might be rather very tedious to count the index there. Well, you can have Python return the index. So the IDX here, when fed again on the input to Oracle, the Oracle returns us true. So just to indicate that working with lambda functions is actually really cool. So we have this oracle here, the oracle that computed a secret and actually computed a function that will tell us when we are right or wrong. You can give tuples of functions, so in some sense you can have too small and too large, also having extra functions, so that it actually you can call oracle, and then the feedback you can also encode this in as two separate functions. So functions can actually return multiple results. Okay, here is the illustration of the Monte Carlo with list comprehensions. So in mathematical notation, it took 3 lines. So here it does a little bit more. I'm generating uniform elements between 0 and 1 using the underscore as an anonymous variable. Then Z is a list of points, a list of tuples, and then I'm having another more complicated list comprehension, the filter. So the main purpose of this Monte Carlo simulation here is to demonstrate a very good example of a filtering. So I have a test. Does every generated point belong to the unit disk? So that is given by this test here on the coordinates x and y. Notice here the nice tuple notation. So every element in that list Z, and here it's also beneficial that Python does not automatically list the feedback, give the result. So here I was explicitly typing IDX after the assignment. So in some sense it's a little bit awkward. I want to use the IDX here, so I have to assign it. But here you see a reason why if you have a list of 100,000 numbers, you do not want to see this. Perhaps for the sake of argument, so I can let me run also every statements. So now I can look at X, but actually I don't want to look at like X. So I want to look at Z. So that was actually the point. So I'm going to insert. So I only want to do this for small lists. So that's why I'm inserting it here. So even for 10 numbers, it's actually not really nice looking. Actually, I do, for one reason or another, I have to, there we go. So I have to execute all of it. So now I see the list of tuples. The tuples are the coordinates of the points. And then I'm selecting from that list all those points. So let me make that again very explicit. I'm selecting all those points that are in the unit disk. It's not so hardly noticeable, but you can kind of see it still that the list R is smaller. And that will of course give me a very inaccurate, although I have already the tree. Not that bad actually. So I have the first leading digit of pi correct. So I will comment this out. So only do this only for small n. And likewise here, only for small n. So typically to correct the Jupyter notebook again, so let's do this for 1,000,000 numbers. See, I'm just running through it and I have 3 decimal places correct. The trapezoidal rule is a better rule than this to compute, and even the trapezoidal rule is not a good way to estimate pi this way. But just for the sake of the list comprehensions, this is a good enough illustration. Okay, now go to the remember tables. So we can store data in functions. And I'm illustrating this here with a dictionary. And I'm going to have an extra option. The option will be the verbose option. So in the exercise, in the last exercise, you will check whether there is an option feedback in options. If that is the case, then you will also return, you will do the same return, but before the return, you will print too small or too large in case the number that is obtained from the user, if that is correct or not correct or not. So here you see now that this is yet another way to implement it. The function now is in complete control of the secret. So it generated the secret if the dictionary was empty. So let me execute this. So if you execute this, there is no error. So I will ask to make a guess. So in some sense, it's a little bit awkward, and it's actually even more awkward that I was lucky. So there's 10% chance that this happens. So now I'm going to type in something different. But you can see that the verbose option makes that the dictionary will be printed. So the data, so there's another dictionary options there. You can print this as well. But here it will print the content of the secret. Of the data that stores the secret. So in some sense, the verbose option is a cheat option. Okay, very good. So I still have almost 15 minutes left. So let me save the corrections that I made to this notebook. And let me go now to the scripts. So there is the make oracle, and I must say that I'm actually do not, that's also a style issue. I no longer like one sentence returns the oracle as a function which returns true or false. So this is a correction. So here it actually generates the secret. So in some sense, after prompting the user, prompting for a secret number. So a documentation string of one line is typically never enough, and here it's even a little bit sketchy. So it returns an oracle. And here I have that the number, so let me save this. So I will save this Python file. So it will return the function. So asking prompting for input in a Jupyter notebook is a little awkward. Doing so in an interactive Python shell is not. So I have my Oracle script. My secret number is 5, so I'm now pretending not to know this. So I will type in just some numbers at random. Ultimately, I'm tired of this and I'm typing 5. So this is the running of the oracle in the loop of this function here. So the oracle is made in the initialization of the loop, and this is another illustration of the break. Each time the oracle is given the guess, and the guess is then compared against the secret number, which was somehow stored inside this function. Okay, so this is the first script that is posted. The second one is also one that typically is run, and you see here the copy and the paste. When I made the Jupyter notebook, I worked backwards, so I have already some scripts that work, and then I try to explain how to get to them. So in some sense, it's unnatural. If you would in real life develop scripts, you would do some experiments, and then when they are looking right, when everything is right, not just looking right, when everything is right in the Jupyter lab session, then you write your script. Okay, so let me quickly run this. So this is the second MC for pi. So we have seen an earlier one. So let me do this for long numbers. And here you see that the script for 1,000,000 simulations, it returns about 3 decimal places correct for the estimate of pi. Not much to this, so let me then go through the third script and last script. So here I copied and pasted what is highlighted here is what is in the Jupyter notebook. Perhaps I should uh, a little bit draw your attention to the main program. The main program passes the value of the verbose flag to the argument of the guess function. So in some sense, it might have looked to you very redundant and a little bit cumbersome that I have the verbose flag, and then that verbose flag also has a value. You could say, well, isn't it enough that there is a verbose flag? But no, it could be that we want to run this guessing game in the verbose mode or in the non-verbose mode, in the hard way or the easy way. And you also see a typical construction in the um, in a loop. So you need some work to be done. And this is also a standard canonical way to avoid the break. The break is very useful. We can break out of a loop anywhere. We can break the body, but it starts to get extremely hard to verify the correctness. Here you will leave the loop as soon as the work is done. So, and here the work is done when guess returns true, when we have guessed the secret. Okay, so the important here is the main program, the main function that prompts the user for the verbose mode. So let me also run this. I will run the Python secret guess. So this is also the second script that I'm posting here. I will run it not in the verbose mode, and now I have to make a guess, and I actually don't know what the number is. Also, I was starting at, but no luck here. So there's not much I can try. And wow, it was 0. Um, so now I don't want to run this anymore in the non-verbose mode. So now I see that I can cheat. I can type in 6 and that will terminate, but let me make the point. So if I type 5, it doesn't enter, but if I type 6, then it does end. Okay, so this is just another variation of the same guessing game, um, where it is now the function that stores the secret, it generates the secret, and it stores it as well. Um, I should say something now about the exercises. So there is the option verbose that was used in the secret guess. So if I go back to the Jupyter notebook, you see here the options. The options, you can check whether feedback is in options. And if feedback is in options, then you check whether the feedback is true. And you do this actually after the user has typed in the number. So if the feedback is in options, if the options feedback is true, so that's actually the test here is the redundant test is if equal true. But if true is true, you don't have to test on that. So in this, so I'm trying to explain here how to make this last exercise. You will give feedback whether the number entered by the user for the guess, if that is too small or whether that is too large. Okay, for the exercise 3, you will use the uniform but the second parameter will not be 1. So if I go back to my Jupyter notebook here, so here my second parameter in the uniform is run, except in the applying of the random angle, you will do 2 times pi, where you can import pi from the math module. Also, here we have two lists x and y that are independent from each other. In this exercise 3, you must make a list of angles, call it a big A, and this will be your uniformly numbers between 0 and 2 times pi. And then you map the function cosine to that list of angles. You get then x, the big X, the list of all x coordinates, x first coordinates of all the points, and then you map the sine function to those angles. So there is a different order of doing things. Here we have twice that we call the random number generator. In the exercise 3, you call the random number generator only once. And you still have to zip them to actually see the final result, the coordinates of the points on the unit circle. Okay, for once I'm not running over time. So there are many more examples that can be generated, but I hope that you get an idea that working with lambdas, working with functions, working with list comprehensions, all of these three different ingredients, so the functions, the lambdas, the list comprehensions, the data structures, they're all different on their own, but when combined together, they make from some very powerful and very useful programs. Okay, in the second half of this session, we will look into files, to manipulate files directly from within a Python session, not via the intermediate DBM files as we have seen earlier. This is a little bit more powerful and more general also compared to other languages. Okay, I hope this was interesting. For once, I'm not running over time. I'd stop here.